Good afternoon, everybody. Welcome to the first webinar of 2016. This is the Agricultural Robotics and Automation Technical Committee webinar number 35. And this afternoon, we'll welcome Dr. Amy Tabb from the United States Department of Agriculture, Agricultural Research Service. And I know there's a little more to the name there, Amy, and I'm going to let you do the proper introduction there. And Amy is going to talk today about autonomously determining the shape of trees for two purposes, structural phenotyping and pruning. This is a problem that is very relevant in the tree fruit industry. Both automated pruning and phenotyping are difficult and very time-consuming operations. And while I'll let everybody read the abstract here on the screen, I just want to make the quick comment that this is work that is being pursued by a lot of groups all over the world. And we're going to see some very interesting results that the folks at the Agricultural Research Service, led by Amy, are getting in this domain. I recall a story from a tree fruit grower in Maryland who said that pruning is kind of like cooking. You can do 80% by following a recipe, but the final 20% really requires a lot of expertise. And he was asking, this was many years ago, whether it would be possible to create a robot that would follow, quote unquote, follow that pruning recipe and do the 80%, thus reducing the cost of pruning significantly. And again, it's something we're going to learn about today. How is it that Amy and her group are doing this? Amy comes from Sweetbriar, the Duke, and Purdue, three excellent schools here in the U.S. At Purdue, she got her master's and her PhD in electrical and computer engineering. And she is now a research agricultural engineer with the United States Department of Agriculture in Kernersville in West Virginia. Not too far from Pittsburgh, if I understand correctly, Amy?
That's right. It's about a 4-hour drive.
There you go. I guess the snow you get is the snow we get. We are connected by that. So with that, I am going to move to the other window where we have Amy's presentation. I have to do this first. Amy, do we have your slides on the screen now?
Yes.
Okay, and let me see if I click here. Is this better? Is it more like full screen now?
Yes.
Okay, excellent. I'm going to close my PowerPoint just so that it's not in the way and close everything else. And I'm going to make this as large as I can. Oops, my apologies. That's not what I wanted to do. Amy, I'm going to have my phone on mute, but you please cue me for the slides, okay?
Okay.
Thank you.
Thank you very much, Marcel, for the introduction and for handling the slide transfer. Okay, we can go on to the next slide. I'm going to give you all a little bit of background about my workplace because many of us are in different kind of context. So the laboratory where I work, as Marcel, is the U.S. Department of Agriculture lab for servants. And then the actual location name is called the Appalachian Fruit Research Station. So we're located in West Virginia, but in just the tip of it. So I put that on the map. You see the little red dot. That's where we are. So not too far from Pittsburgh, as Marcel mentioned. And we usually fly out of the Washington D.C. airport, so we're very close to Washington D.C. And the Appalachian Mountains are the ones on the East Coast. So we do have some mountainous regions here. Okay, next slide, please. So this lab has a lot of different disciplines contained in it, and it's generally concerned with the problems of temperate fruit production. So that means apples, peaches, plums, pears, and we also do berry crops. That would also include cherries, but we don't happen to have anyone working on cherry at the moment. So there's an entire ecosystem of people to work on these problems. So we have entomology, pathology. There's two molecular biology groups. One is pathology and stress, and the other one is genetic improvement. Then we have a small fruit horticulturist, some plant physiologists, and then my engineering program. And I have an engineering technician and a horticultural technician, but I'm the only research scientist in engineering at this location. Okay, next slide, please. This is a roadmap of the talk. So I'm going to give a description of the two problems that I'm working on, dormant pruning and structural phenotyping. And then I'll give an overview of the shape estimation system as it is today, some results, and then future directions. Right, next slide, please. So dormant pruning of apple means selectively removing branches in the winter when there are no leaves. So on the left, I show a freestanding tree, which was very common in this area about 40 years ago, and on the right is our high-density trees with a trellis. Now, pruning a freestanding tree would be extremely difficult to do with a robot, so we're not concerned with the freestanding trees. Instead, we're working with the systems on the right in the high-density system. And next slide, please. So I'm going to tell you in particular which system I'm using. The horticulturists are pretty intense about this part. So it's a tall spindle training system, and it has one central leader or a trunk. They're considered no permanent branches, so in some systems you leave a permanent scaffold on the bottom, and this is not one of those. And on the East Coast, this has been actively researched for 10 to 15 years. Started in New York and now in Pennsylvania. There's a lot of work on this system. And on the West Coast, they're able to use plant growth regulators like apogee, but for various reasons, on the East Coast, the growers are reluctant to do that. So the trees on the East Coast tend to be bigger and more vigorous than the trees on the West Coast in Washington State. So these trees are at the Penn State Experiment Station in Biglerville, and they're spaced 3 feet in the row and then 14 feet between the rows. Okay, next slide, please. And some horticulturists have been developing recipes for pruning so that you can get the 80%, as Marcel was mentioning earlier. And most of these rules are based on the branch diameters of the secondary branches relative to the central trunk's diameter. And then the second level would be branch angles relative to the trunk. And the general idea is that you determine the branch diameters of all the secondary branches, and then you sort them and you remove the largest ones until you reach a certain ratio. And then you remove excessively upright or excessively pendant branches. So Dr. Jim Shoup, he's at the Penn State Station. He's been developing these rules and doing some field studies to determine what the best selection of rules are for fruit productivity. Okay, next slide, please. And so I'll talk more about the second problem, structural phenotyping. So one of the molecular biology groups here is very interested in the genetic processes of plant architecture. So here I'm showing some Arabidopsis plants. Arabidopsis is just a mustard plant. It's very easy to transform, so the biologists use it quite frequently to test out ideas. So these plants have been manipulated. Well, on the left is an unmanipulated one, and on the right is a manipulated one, and you can see how different their architecture is. And they have to use a support post to keep one of the stems up, because otherwise the stems just want to lay on the ground. So it seems that genotyping is becoming cheaper for these biology groups, but phenotyping still remains really expensive. Next slide, please. So they want to apply this work in Arabidopsis to fruit trees, and so they want to determine if fruit trees can be produced with desirable structural characteristics. One of the big things they're considering is if you could make a tree with a very narrow canopy, then it would help with automation, for instance. And so in order to determine that, they need the phenotypes and genotypes. And as I said, genotypes are getting cheaper, but phenotypes still are hard to determine. So currently, they have students go out in the field and they measure a sample of the branches, and they get things like branch diameter, angle, and length, which is very similar to what's needed in the pruning problem, by the way. But different students will measure different ways. It takes a ton of time. The data is usually messy, and so then they have to sort out those issues while they're lining up the genotypes and the phenotypes. So they want something faster and more precise. Okay, next slide, please. So these are some examples of trees in the breeding program here with different phenotypes. You can see the ones on the right have very small branch angles and are generally upright, whereas ones on the left want to have more spreading branch angles. And this work is supported by U.S. National Science Foundation grant with some molecular biologists, Kanang Zhu at Cornell, and then Christopher Dardick is here at this lab. So all the plants are from the programs of Chris Dardick. Okay, next slide, please. So since shape estimation is needed for the pruning task as well as the structural phenotyping task, I'm going to talk about a general system for working on both of these problems. But eventually, the systems would need to be differentiated, because in phenotyping, precision is more important, but runtime is not so much of an issue. Like the data could be computed over a week, say, and that's not an issue for them as long as it's computed well and without human labor. Whereas for the pruning problem, it has to be very fast, and resolution may not be as important. So we created here a computer vision system for three-dimensional shape estimation. And so it does use a robot and with cameras for the vision, and these are just color cameras. And then the third component are algorithms developed here and a background trailer. And I'll show you some pictures of what we have. So next slide, please. So this is our outdoor mobile robot platform. So it's self-propelled, and we have a traditional 6-degree of freedom arm mounted on the platform. It has a 1,300 millimeter reach. And so I point out the camera on the left-hand side, and then on the right I show you where the computer and the controller is. So we were able to use this system last season to get some data, and we're in the process of changing that around a little. Okay, next page. Next slide, please. And this is the background trailer. So what we've done is we, instead of trying to segment the trees that we're looking at in the current row from further rows, we have a trailer connected to something like a John Deere Gator that pulls it so that we have a nice background. And so we chose the color blue, and this shows how the robot fits in the row with some what we call our easy trees, because they're super sparse. Okay, next slide, please. So in order to generate the 3D shape, we use silhouettes as features, and this is an overview of how the system works. So first, we acquire images. We move the platform in front of a tree, and we have the robot run a sequence and capture images at different points in that sequence. And because we're using the robot, we can compute where the camera is at different points in the sequence. So we have essentially calibrated cameras for each stop of the robot. And then do a simple segmentation, the 3D reconstruction step, and then finally curve skeletonization. Okay, next step. Next slide. Oh, there you go. Okay. So this is the first step, is acquire images with the robot. So these are examples of some images from one stop of the robot. And you can see with even a wide-angle lens that we don't see very much of the tree at one stop. That's because of where the robot was placed on the platform last year. But we hope to mitigate that this year. I'll tell you a little bit more about that later. And as I mentioned before, for each stop we know where the camera is in space. And for large trees, we get 96 images per tree. Okay, next slide. All right, and then I just do a very simple segmentation. So the philosophy of this work is that the segmentation is never going to be perfect. So I accept some error at this step, and then on the next step deal with that error in the reconstruction stage. So it's just a pretty simple threshold-based approach. So I just convert it to hue, saturation, value, color space, and locate the blue background and the sky, and then do some simple shape processing, and then find the tree candidate regions. So on the left is the raw image, and on the right is a segmented image where white is where the tree is. And you can see that there's some error there, particularly with the ground are the biggest ones. Okay, next slide, please. For the three-dimensional reconstruction step, the reconstruction problem was framed as a shape from inconsistent silhouette problem. So what that means is that there's an assumption that the segmentation error is present, and also an assumption that there may be small camera calibration error. And then the way I thought about this work is that you can represent the difference or the mismatch between any shape and the input silhouettes as a cost function. So then to find the best fit shape for those silhouettes, you minimize the cost function. It's not quite that simple, because to minimize that cost function is an NP-complete problem. So I find a local minimum that makes sense in this reconstruction context. And if you're really interested, there's a paper about it at CVPR a couple years ago. Okay, next slide, please. So as I mentioned, small camera calibration, the system can tolerate that pretty well. But when I was working with the robot a couple years ago, I noticed that sometimes there are the state-of-the-art methods for robot calibration would give you some values that resulted in poor reconstructions. So I also ended up working on the robot world hand-eye calibration problem. So move to the next slide, please. So the robot world hand-eye calibration problem is modeled as AX equals ZB, where A, X, Z, and B are homogeneous transformation matrices. And B is from the robot controller, so if you have X and Z, you can determine where the camera is, which is what I need for the reconstruction algorithm. So there are different ways of computing X and Z, which are the unknowns. And so I came up with a new method that made sort of more sense for the reconstruction context. Next slide, please. And so this shows some of the reconstructions using the same images, just different calibrations. So A is a method from '94. You can see in this peach tree that many of the branches are not connected. And then the B is from '98, and that's sort of like a null reconstruction. The Hirsch method in 2001, it does a better job than A, but also there's some broken branches, and the new method results in a more continuous shape than the others. So that's also in a paper from Iris in the fall. Okay, next slide, please. So here's some of the reconstructions using this shape from inconsistent silhouette approach. So on the left is a Gala tree. I think it's about 4 years old with a support post. And on the right is a Fuji from Penn State. So the great thing about dormant pruning is you can just cut a tree down and put it in a truck and bring it into the shop and work on it. So this is one of the trees we brought down from Penn State to get an idea of what kind of trees they had there. And there are some artifacts that result from using silhouettes. So you can see in the top of this Fuji tree on the right some weird noise and thicker regions than would have been in the original tree. And unfortunately, I didn't take pictures of these trees. But anyway, okay, next slide, please. So this gives the result of the curved skeletonization step. And so the reconstruction is on the left in blue, and on the right is the curved skeleton. And it's able to deal with the noise of the surface of the reconstruction, and generally gives a good result. Okay, next slide. And this is for the Fuji tree. So you can see that noisy region up at the top, the curved skeletonization method does a pretty good job of only finding what would be true branches. And that work is currently under review, so sorry, no paper for that one. Okay, next slide, please. So here's an overview of what the running times are for the pruning application. And the run times are highly dependent on a number of factors. So how many images are you using? What's the size of the images? What voxels? What's the final resolution that you want to use? And the quality of the segmentation. So if the segmentation quality is really high, there will be less ambiguity, and the search concludes more rapidly. But generally, the acquisition step using the robot takes 1.5 minutes. Segmentation takes a minute, and then reconstruction is a variable, but around 4 to 6 minutes for a large apple tree. And then the curved skeletonization step is the fastest at 5 seconds. So in particular, these times are for 96 2-megapixel images, and the final voxel size is 5 millimeters for the mature apples. Okay, next slide. Here's some results for the phenotyping application. So these are transgenic plum in pots, and the final voxel size on these is 2.5 millimeters. So you can see on the right are the pillar or the PTAC trees, and you can see that they're more upright, and the method was able to generally capture the structure, though these trees have very, very thin branches. So that's a big struggle with these, because in the pruning application, you're only interested in larger branches, but in the phenotyping application, they're interested in the small details. Next slide, please. And these are another class of plum trees. So you can see they have more of a spreading growth habit and do some sort of strange things with branch angles compared to normal plum. Okay, next slide, please. So this project is, we've done 1 year of outside tests, and it's still winter here, so we're going to get a second year of field tests in soon. But the future work on this project is to continue refining the algorithms and the implementation to get decreased runtime, especially for the pruning side of things. And then quantify the accuracy of the system with respect to the characteristics that most people are interested in. So diameters, angles, and other features, probably curvature for the phenotyping one. And then we're going to change the mobile platform to allow a greater variety of camera views. Next slide, please. So here's part one of the equipment transformation. So whereas the robot was mounted on one side of the mobile robot platform, we have a scissor lift, and then there will be rails on that so we can move it back and forth and up and down and find out what the best location of the robot should be for next year. And then the driver will be changed from where he was last year to up above the engine. Okay, next slide, please. And then for the National Science Foundation grant with Cornell, we're sending another unit to them. So we get some things from government surplus here, such as this generator, three-phase generator, and this small truck. So we are able to get those things from surplus, and then we'll put a robot on the back and send it to Cornell so that Kanang can get images of his transgenic apple for the project. Next slide, please. Something that, in terms of the structural phenotyping application, something of interest is tracking change over time. So they're interested in how have these plants changed over time, and also why have they changed over time. So on the left is one of the trees, the plum trees in this pot before it was planted, and then on the right is after it had been in the ground for 6 months. And that's a possible future application of this work. Okay, next slide, please. So I have the citations of where some of this work has been published, if you want to look up some more details. And that concludes my presentation.
Amy, thank you very much. These are very, very, very interesting results. I have a few questions, but why don't we let other folks jump in first and ask their questions?
Okay.
So there's a question here on the chat window. Do you have the chat window open there?
Yeah, okay. So I just saw on the new one from viewer 10. Okay. Could you please comment on the choice of using lasers as opposed to, using cameras as opposed to something like a laser? Okay. So with laser, you get the flying pixel problem, and also with really sparse objects like a tree, it's difficult to capture small details. So I think that laser could work, but it would take. It's not an easy. It's not particularly easy to use laser. I think it would take a lot of work to get it to capture those small details, and maybe do something like super resolution. So I haven't used laser a great deal, but cameras are extremely cheap, and you don't have to worry about this flying pixel problem. So that's why I started using cameras instead of laser. Okay. Zach at NREC says, what's the pattern of use camera trajectory look like? So in general, the camera positions are pointing towards the row, and because we use a stationary unit, we don't go all the way around the tree. We're just looking from one side, and so I just alter the angle slightly to get some different viewpoints. But I guess you could say it's sort of like a grid pattern on one side of the tree. Okay. All right, and then the next question is, your trees seem to be mostly bare. How do you deal with crops and trees that have more foliage? Well, for dormant pruning, there's never leaves. So I'm not, this system is not meant for trees with leaves. I think that if you did want to use this system on trees with leaves, you could alter the shape from inconsistent silhouette approach to use something like a Connect, like an RGBD sensor. And I have some ideas for how to do that, but I haven't gotten there in terms of working on it. Okay.
Amy, here's another question. Maybe I missed this, but it is very difficult to get ground truth for these measurements. right? You're getting a measurement and they seem reasonable, but how is it that how can you tell that they are good if even getting the ground truth or the true shape of the tree is very difficult?
Yes. I mean, difficult to impossible to get the actual shape
Right.
of the true tree.
Yeah, I didn't want to say impossible, but that's
no,
the right
I think
word.
it's impossible. So one thing that is planned is to do ground truth in terms of branch measurements.
Mm-hmm.
It takes a lot of bookkeeping. We did something last year which wasn't quite satisfying, but we plan to work with a horticulturist on that. And I think we did like distance. We identified the branch locations using distance to the ground or something like that. So it's not very elegant and it's sort of difficult. But we plan for the pruning application, to concentrate on branch diameters and compare the computed branch diameters with those of a human. Does that answer your question?
Yeah, and I was wondering if it makes sense as well to, for example, have Jim Shoup and the robot right side by side looking at a tree, and Jim Shoup would look at a tree and with his recipe in hand he would say, I would prune here, 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 and here. And then let the robot with the camera and the algorithm do its work, and the system would say, I would prune here, 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 and see if they match. And that's a different level of comparison with ground truth. It's more of a horticultural ground truth.
I see. Yeah, though I went to a pruning workshop with Jim and another person, I don't remember his name, but they argued good-naturedly most of the workshop about how they disagreed. So it's a little difficult to compare a human's idea of how they would prune, even when they're given a set of rules, because they were both going off of rules. But yeah, that's a good idea too.
Very nice. There are two other questions on the chat window.
Okay. Well, I used the blue board background to prevent the cameras from seeing the other rows. So we've got multiple rows, and when the trees are bare, you can see like 8 other rows. So I don't want to catch them in the cameras. And then it makes segmentation very easy because I'm using a silhouette-based method. Viewer 8, do you measure 3D positions of a tree? If so, what kind of algorithm do you use? I'm not quite sure. Is this similar to Marcel's question? I mean, you can unmute and clarify if you're on the phone.
Yeah, so the person who asked this question, please feel free to unmute and ask the question in a different way. I wasn't clear about that myself.
So viewer 8, do you want to ask the question on the phone? I don't quite understand it from the text.
Not sure if that's coming, but if not, I suppose that person can send an email later. All right, Amy. Okay, we got a comment here. We will mail later. Very good.
Okay.
Amy, again, thank you very much. First webinar of the year. I think we are off to a great start. And I invite everybody to join us in March, where Jeff Hollinger from Oregon State University is going to talk about his work in agricultural robotics. Jeff also comes from a technology background. He got his PhD in robotics here at Carnegie Mellon. So is another talk on true robotics, true roboticists like Amy, applying their skills and their techniques to agriculture. Amy, thank you again. Good afternoon, and for everybody else out there, thanks for participating.
Thank you very much, Marcel.
Bye-bye.